In the last slide, we turned the integral along the real segment into a contour integral running along the upper bank of a branch cut. To use a residue theorem, we need to close the contour. And here comes the next general rule. Whenever you deal with the integral along the finite segment, you should always close the contour, turning it into a dumbbell-like shape, like this. Let's take a closer look at our closed contour. It consists of 4 parts. The first part, let's call it C+, is the linear integral running along the upper bank of a branch cut. It's nothing but our initial integral. Now its lower counterpart. It's the same type of integral, but running obviously along the lower bank of a branch cut. And the only difference from the first one is that its integrand should be taken at points z equals x minus I0. Together, these two integrals form the bar of our dumbbell. Then there are weight plates, the infinitesimal circles round the branch points. Let's call them epsilon 1 and epsilon negative 1. In fact, both these circular integrals are vanishing when the radii of these circles are tending to 0. I'm not going to waste a precious time proving this right now, postponing the proof till the end of the computation. But actually, whenever you deal with the integral converging at its endpoints, those kind of circular infinitesimal integrals always vanish. Think about it yourself and try to convince yourself why it's always true. As a result, our closed contour integral is turned into a combination of 2 linear integrals along the upper and lower banks of a branch cut, from -1 to 1 of f of x plus I0 dx plus from 1 to -1 of f of x minus I0 dx. As I pointed out earlier, the first integral is just our initial integral. So our next goal is to try to express the second integral via the first one, that is the initial one. But the only difference between the two integrals is the difference between the values of the function of f of z on 2 different but infinitely close banks of our branch cut. So what we are going to do is we will relate the values of our function at point x minus I0 to the value of our function at point x plus I0. We did a similar exercise at least once the last week, so now you can appreciate the effort and time spent on it. So what we do is we take 2 points, x plus I0 and x minus I0, and connect them by some contour. For example, a circle to the right of our branch cut. And next, we trace the changes of the arguments of the constituents of our f of z function. So 1 minus z number is represented by the arrow, which rotates by 2 pi into a clockwise direction. So the delta argument of 1 minus z equals negative 2 pi. Now 1 plus z arrow undergoes an infinitesimal rotation, so the change of the argument is simply 0. We discard it. So the total change of the expression under the cubic root is minus 2 pi plus 0, which is simply minus 2 pi. And then recalling minus 1/3 power coming from the denominator of our multivalued function, we conclude that the change of the argument of our multivalued function is minus 1/3 times minus 2 pi, which gives 2 pi by 3. Finally, we establish the relation between the values of the function at points x minus I0 and x plus I0. f of x minus I0 is simply f of x plus I0 times e to the power 2 pi I by 3. Hence, we can rewrite the integral along the lower bank of a branch cut using this relation. So IC minus equals the integral from 1 to negative 1, f of x plus I0, e to the power 2 pi I by 3, dx. Now factoring out this constant e factor and changing the limits of integration into a more natural one, thus earning additional minus sign, we get minus e to 2 pi I by 3 times the integral from negative 1 to 1 f of x plus I0 dx, which is nothing but minus e to 2 pi I by 3 times the initial integral. So one more goal is achieved. We expressed our closed contour integral via the initial integral, namely it's equal to our initial integral times 1 minus e to the power of 2 pi I by 3. And now we can employ the Cauchy residue theorem to compute the closed contour integral. As we remember, the internal region inside the contour is the one which stays to the left as we go around the contour. Paradoxically, in this situation, the region which stays to the left is their outer complex plane. And that means that our closed contour integral is equal to 2 pi I times the sum of the residues in the outer complex plane. But if you look carefully, there are no poles in the outer complex plane. So the only available and possible residue is the residue at infinity. So our closed contour integral will be given by 2 pi I times the residue of our integrand at infinity. We will complete the calculation in our next slide, but for now I just want to stress that at least ideologically the problem is solved. Once we are done with the residue at infinity, we have this integral in our pocket. So let's complete the calculation on our next slide.